post this solution in plan to post this solution in the Blackboard, of course. Let me begin with a word of prayer. So, Heavenly Father, we thank you for this semester and for this time we've had to study your creation together. I just pray you be glorified in what we do this day. Lord, I pray. Amen. All right, so this was your quiz of review, formerly known as final exam from the first time I taught abstract algebra, namely 2016. And if I can find my laser, I will begin pointing at this. Not yet found my laser. Oh. Thank you. I need to, I'm gonna put three together. I have my tricolor laser, but I haven't got to it yet. All right, so it's more fun. Let's see here. So if we look at Q adjoin the cube root of 2, I said calculate the degree of the extension of f over q and find a basis. So this one's like taking candy from a baby that does not like candy, although those are in short supply. This is an irreducible by Eisenstein. Yay! And consequently, that means that it is a degree 3 extension then, and you can use 1 cube root of 2 and cube root of 2 squared as the basis. All right, any questions? Okay, I think that one's pretty cut and dried. This is irreducible by Eisenstein, p equals to 5. Well, that's friendly. This is irreducible because if you reduce it mod, I can't even, I gotta put on my glasses. This is sad. 2, yes. So we have it 0, both 1 and both cases, which means it's going to be irreducible over Q by the theory that we talked about. Now, warning: be wary, be vigilant, be prepared. What if it's quartic? Yeah, if it's quartic, then right. Well, you can't use it. You can't just test for zeros, right? If you test for zeros and you find out that there's no zeros over the reduction field, then what does that tell you? That tells you that there's no linear factor, right? But the quartic could still split into a pair of irreducible quadratics. So then you got to go looking to find, are there any irreducible quadratic factors? Now, if you're working mod 2, that's not too bad. There's only one irreducible quadratic mod 2. It's, what is the irreducible quadratic mod 2? X squared plus x plus 1? I think that's it. X squared plus x plus 1 is irreducible mod 2. And I think that's the only, well, there's only monic irreducible. There are only monic quadratics, right? Mod 2. Can you have a non-monic quadratic over 2? Over Z2? I guess not. But if you start looking at how many irreducible quadratics there are over higher things like Z3, I mean, there could be more than one of them. I can't remember. I think there are 3 irreducible quadratics mod 3, if I remember right. I forget, something like that. But, you know, if there's a problem on my final, which is like, find all the irreducible quadratics over Z mod 3, and then I have a question later that's about factoring a polynomial, and Eisenstein fails, and it's quartic, and you find that there's no zeros, mod 3, maybe the point of the earlier problem was to already have on hand the irreducible quadratics, right? So, you know how I make tests. Beware of stories that I'm telling amongst problems, right? So, oh, hey, this one, that's a very popular question, isn't it? This one's like in every homework set. I think I always ask this question in homework or on a test. You like that question? But everyone knows how to do that question, so it's not really a fun question for the final. I don't really learn anything from putting that one on the final, right? You guys don't learn anything. You've done it before and you understand it. What's the point of putting that on the final?
Final is showing what you understand.
Final showing what I've learned.
Final showing what you've learned.
It's showing what you understand.
So you guys are telling me you don't want to learn more.
I do not want to learn new things. That's what next.
Don't want to learn new things on the final.
You have all next semester to teach us new
You have,
things.
oh, dang it.
You have the four of us next semester to teach us new things.
But this row, you have this row in abstract 2 next semester.
Excuse me, you're being so. You said this row. Oh, I thought you said like yeah.
That's why I said, oh, Emily,
You have all next semester to teach us things.
bumped that.
Ah. All right, well,
Oh, I have a question on the next one.
okay.
Is there a slick way to find all of the order 2 elements other than brute force?
Oh, an S5?
Because
If
I
you're,
forced it, but there's 22.
yeah, if you're better at count,
22, I found all of them.
if you're better at counting than I am, you can do it. What's that? It's wrong?
There's 25.
There's 25?
There are 25.
See, like I said, I'm very bad at counting. I warned you guys. If there's counting involved, be suspicious. What did I miss? Good luck. Good luck finding. Good luck finding the transposition I missed. Right? But the larger point here is that even with your 25, we definitely don't have as many elements of order 2 as D60, which has how many elements of order 2? Yeah. So it's, what is it? 5 choose 2?
Which one?
How did you guys get 25? Brute force. I do think there's a combinatorial way to, because you're picking 2 numbers from 5, right? And they can't be repeated.
It'd probably be, what, 5 pick 2 divided by 2?
And why would you say divided by 2?
Because 1, 2 is the same as 1.
Very good. Right.
Yeah, do pick instead of choose.
Pick instead of choose.
What is it also valid
5 pick 2 divided by 2.
to say that an element with order 60 in S5 would have to be able to be factored into disjoint cycles of order 3, 4, and 5, so that at least comes.
Oh, wait a minute. The other, hold on a second here. 5 choose 2 is 10. Great. Hold on to that thought.
Right, that's
You're fine.
transposition.
Yeah, but the order 2 elements is also products of disjoint transpositions. So then that's, how do you count those? You picked 2, then you've got to,
I got it. Okay. No, I believe in Emily. Okay, so it's 5 pick 2 gives you the sets of like things that are the sets of things that are 2.
this gives us single,
That gives you, the 1 to the
single transpositions, right?
And then you divide it by 2 so you don't get repeats. It's just 5 choose 2.
No half. It's either 5 choose 2 by itself with no half, or 5 pick 2 divided by 2.
These guys.
Yeah.
There's 10 of them. What's 5 choose 2?
5 choose 2 is 10. So no 1 half.
Oh, no 1 half. Okay.
If you do 5 pick 2, you divide by 2.
Oh.
I think I choose that.
And
So if you're, so if you're doing this, how do you count the number of these guys? Ones like that with a disjoint, obviously.
Well, each number happens 4 times in those 10. So then to have one that's disjoint, you would have 1 paired with 5 others, I think, or something like that.
So there's 10 options for this. Those 10 options.
Well, they have to be disjoint, so like if you choose one of them, then that only leaves how many left that you could put with it? Only like
oh yes, that gives you
2
5
or something
options
like
with
that.
the other one. And then you divide it by 2. Yeah. Yeah, so there's 5 options for
Well, that divided by 2 gives me 15, and 15 plus 10 is 25.
There are 15 of them.
I don't know. I'm not good at this stuff. I'll be honest. I'm not. Counting is not my strong suit. I have, at various points in my life, come up. I have, in the past, found a really clear algorithm for counting these things, but it left my brain, and I have since forgotten it. And my apologies. No, I don't have anything. Look, I mean, I got 22, right? So.
Yeah. But
Now, listen, this is, I mean, maybe pick something easier if you're going to pick at this anyway. I mean, like D60 versus S5, you know, there's other things that D60 has that maybe, I don't know, there might be other ways to pick apart it. I don't know. I just gravitate towards elements of order 2. Anyway, that is one way to attack it. But all the non-isomorphic abelian groups of order 36. So you guys happy with this? All right. I mean, you should be relatively happy with my answer to your last question, because you can read from that. I'm not going to be like, how many 3 cycles are there in S400? See, if I was a person with more deep-seated love of combinatorics, I could ask such a question. But I definitely have not given you the tools to answer that question, have I? So this is the silver lining of me not having taught probability and statistics anytime recently, except online, which kind of is different. So. No, I have not taught it. Well, I mean, yeah, I taught it online. And let's face it, in Math 201, we're not going to be counting the number of 3 cycles in S400. So. Any questions about this one? So the Wrangle 3, or the other notation, which Liam objects to, for the principal ideal generated by 3, 0, 6, 9, and 3 additively, right? And that gives us how many cosets? So that's a subgroup of order 4, which means that 12 divided by 4 is 3. We're going to have 3 cosets, namely the ideal, 1 plus the ideal, and 3 plus the ideal. Yeah. And so we can create addition and multiplication tables for this factor ring. Here they are. Is it a cyclic group under addition? Yup. You can generate it with either one of those guys. On this one? Yeah, I think it's supposed to be a 2. Unless you want to set 2 equal to 3, but that seems perilous. Is it an integral domain or field? Yes and yes? All right. Yeah. I mean, I guess the right way to answer that is, if it's a field, it's automatically an integral domain, so let's just answer whether or not it's a field. Right?
I have a question. If it's maximal, is it necessarily prime?
If it's maximal, is it necessarily prime?
We have proven that
Well, if it's maximal, then the quotient ring by a maximal ideal gives me a field. And since a field is an integral domain, yes, maximal implies prime.
for some reason I don't feel like that necessarily
I'm just using the theory.
correlates right with that. Okay.
Yeah. But no, we have, there's a proof. I mean, I can go back, but you can also glean it from the main theorems we have about maximal and prime, namely that how's it go? A commutative ring mod a maximal ideal gives us a field. Commutative ring mod a a prime ideal gives us an integral domain. So since a field is also an integral domain, that means that maximal must also be prime, but not vice versa, because not every integral domain is a field. So, yeah. Now I said it would be, I said it would, what I'm trying to say here is if you start with field, asking yourself the question, is it a field or not? If you answer yes to that, then you already know it's an integral domain. If you say no, it's not a field, that does not show you it's not an integral domain. It just shows you that it's not a field, right? So I mean, I don't know. This problem is so simple. I don't know where to start or stop. Is 3 prime or maximal? It's both prime and maximal, because Z mod that is both an integral domain and a field. All right. Decide if x given below is a unit or zero divisor in Z300. All right, so x equals to 40 is a zero divisor because it is not relatively prime to 300. And we have learned that the units of Z300 are those numbers relatively prime to 300. And let's see here. Oh, I show you. So like 40 times 30 is 0 mod 300. And yet, you know, this means that 40 is a zero divisor. Here's some explicit proof of it. Yeah. Like I said, prove it. So, in this kind of problem, to be safe, I think I probably would be content for a student to tell me it's relatively prime to 300, but I'd be much happier with the student if they showed me that it's a zero divisor by just producing its nil factor. It's the number which multiplied by it gives you 0. You know, that's a better answer in my estimation here. Debatable, but just telling you. Now, so again, I probably wouldn't take off points if you didn't write this, if instead you just said, well, the greatest common divisor of 40 and 300 is 20, which is not equal to 1. Therefore, 40 is not relatively prime to 300, which goes to show you that 40 is not in the units of 300. How about 37? Well, 37 is prime, isn't it? And it's not a factor of 300 either, is it? No. And so we can run the usual song and dance, which only has got 2 steps in this case. And out pops the inverse. Now, I think this number is sufficiently large that you probably couldn't have guessed. It's unlikely a student would have been able to guess that the multiplicative inverse of 37 was 73 in Z300. That would take a lot of numerical effort to just bang through directly. So it's important that you know the Euclidean algorithm and how to do the back substitution, right? Because if you don't know that, you can't calculate this. Oh, you disagree?
No, I said you just switched the numbers.
Isn't that cool? Right.
It's one of the emerps.
It's one of the what?
The emerps.
The,
Backwards, it's a prime whose reverse is also a prime.
it's an what?
An emerp.
An emerp?
Yep.
Is 73 prime?
Isn't it?
I don't know. Is 73 prime?
I think so.
Oh.
From what I remember.
Huh.
It would have to be, because that has an inverse. 37 is an inverse.
No, it's legit. I watched a video on it.
Huh. Cool.
I watched a video on sequences of numbers and you had to guess what the pattern was. Some of them were not legit, but that one was legit. Emerps.
Awkward. Let's see here. I've not been investing enough time in inventing fictional relationships in recent years. I need to work on this. But anyway, I do. Z88 is an additive group. Find the order of 11. All right, the subgroup generated by 11. Okay, so 8 times 11 is 88, which is 0. In other words, the order of the element 11 is 8, right? And in particular, here's what it is. And so since the order is 8, we know that anything selected from U8 if you take that any power in here of a given generator for 11, it will generate the whole thing, right? So since 11 generates 11, I can take 11 to the first, which is 11. I can take 11 cubed. I can take 11 to the fifth. I can take 11 to the seventh. Any of these are potential generators for this cyclic group of order 8. In summary, 11, 33, 55, and 77 are actually generators. So, what? Oh, I was thinking exponentiation. I should just think multiplication here, right? Because it's an additive group. And multiplication is exponentiation in this context. So sorry.
Well, yeah.
Hmm.
I don't know, I just wondered, I guess, what you thought of this. So I just proved 22, 44, and 66 weren't. And obviously 0. So then Euler phi of 8 is 4.
Yeah.
And so
Process of elimination.
there have to be 4 generators.
That also works, yeah.
Okay.
Yeah. I think my way is easier, though.
No, yeah, I agree. But
If I did it right.
I did not think of it.
Let's see here. U150 is isomorphic to Z2 cross Z20, question mark? All right, so U150, so 150 is 6 times 25. I chose 6 and 25 as a factorization because these are, of course, relatively prime, right? And as such, if we have a product of relatively prime integers, then theorem said that that was isomorphic to U6 Cartesian product U25, the direct product of these groups. And, well, U6 is Z2 and U25 is Z20 by our usual technology.
I'm sorry, not problem 9.
Oh.
Problem 10.
So U150 is in fact isomorphic to Z2 cross Z20. Yay. All right. Trying to think what else I could say about that problem. I don't know. I personally, I really like these kind of problems because they really, it's nice to kind of get to this point of looking back and realizing you've really learned something. Because if you're not in this class and you see this question, does it mean anything to you? I mean, I don't think you have any hope of answering this kind of question. Even if people explain what the symbols mean, that doesn't help. I mean, you can say, oh, it's just jargon. That's not even it. Like after a person has fully explained the problem to you, short of developing the theory that we've gone through and understanding it, it's nearly impossible to solve such problems. Unless you're a number theorist, in which case it's all number theory. So whatever. Those people are annoying. I jest. Anyway, I don't think these questions have been number theory for quite a while. Number theory's moved past these questions to more interesting questions some time ago. But anyway, so how many automorphisms of Z75 have order 20? So the critical idea here is that the automorphisms of Z75 we can prove. In fact, this makes a pretty good test question. Prove that the automorphisms of Zn are isomorphic to Un, right? That's been a question that has appeared on previous tests in previous years. But anyway, you can prove that Zn is isomorphic to Un. And as such, we can analyze U75 more easily because we know that that can be broken into U3 cross U25, which is Z2 cross Z20. And then the question is, how many elements of order 20 are there in here? And this involves counting, which means that my answer may well be wrong. Let's see here. So let's see here. If I can get it right. Now, so I either need a generator of Z20. How many of those are there? What's Euler phi of 20? It's Euler phi of 4 times Euler phi of 5, right? 5 is 4. 4 is 2. 2 is 8. 8, okay. So there's 8 generators for Z20. And then So I can either have this, I should get 16, right? How did I get 20?
Because you counted
I, the least common multiple of 2
Yeah, I was
and,
wondering about that.
the least common multiple of 2
Or
and,
just the top line.
the
is
least
like
common,
multiples.
the least common multiple of 2 and 10 is 20. Yeah. Oh well. I hope I didn't give anybody a bad grade over this. I don't know. Maybe you should contest my final grading. I don't know. Sadness. Yes, obviously that should be, what do we say? 16. Thank you. If we've learned anything this semester is that you can't count on me. I mean that I can't be counted. I shouldn't count. Metaphorically, that seems kind of unpleasant. I don't know. Dn is that the dihedral group, the usual terms and conditions. Aha! I asked you to prove our happy relation, right? And that anything has order 2. I think once you've proved this, proving that is actually pretty easy. So proving this is induction, right? So I start out by, I start with the definition, which gives me this, which gives me that. So there's k equals 1. Then I suppose it's true inductively for 1 through n minus 1. And then I consider x to the k plus 1 y, which is xxky, which is xyk to the, what? Hey. What did I do?
How did you get from the first statement past the first arrow?
This one?
No, all the way to the very top. xy times xy equals 1 to, how did you get there?
That's x, y, x. I multiply both sides by y.
Oh, okay.
Oh, wait. I think your middle line is wrong.
This one, right?
Yeah, you say
Yeah,
x. X to
after I say no help?
Yeah, because you say x to the k, y is equal to x, y, x to the k minus 1.
Yeah.
But it should be x to the negative k.
Yes, it should. Right.
Because then when you
Yeah.
move the other x over,
Then
it
you got-
becomes x to the negative k plus 1.
Exactly. So, which I probably did right down here,
Oh, right.
but in a slightly different order. I somehow convinced myself that, oh, you have to do it in the other way, because this way doesn't work. When in fact, this way works just fine if you don't make this idiotic, wrong mistake stuff. Doofus. Anyway, cross out this line. Zzz, burn it from the record. All right. Let's see here. Oh, and then by induction, we've got it for all k, right? And then if you look at this times that, we use the laws of exponents that we just proved, which was that we can flippity-floppity. Then we get x to the minus k, x to the k, y on the outside, which gives us yy, which is 1, order 2. Woohoo! So that wasn't bad. So let's see here. We have this subgroup of order 2 of S3. Supposed to show it's not a normal subgroup. So what do? What did I do? Oh, okay, right. So I just showed a left and right coset which don't match. So 1, 2, 3 on H gives me that. H on 1, 2, 3 gives me that. These are not equal, therefore H is not normal. So there's a kind of funny juxtaposition here, right? So showing, when we were trying to prove normality, often it's convenient to show that G inverse HG is a subset of H again for all G. That's often like a convenient method of, and that was our definition of normality of H, right? But when we're disproving that something is normal, maybe just checking that the left and right cosets for a specific choice of representative is a nice method of disprovenating. Anyway, there it is. What's up next here? Oh, I foolishly was trying to see if the students knew what a function was. Oh, why do I bother? So phi from Z9 to Z6, defined by, we map the 9 coset, the 9 residue class with representative x to the 6 residue class with representative 2x. Then the question is this a well-defined function? Oh, prove it's a well-defined function. So I suppose x like that, which means x prime is equal to x plus 9k, plug it in, I get an extra piece of 18, which goes to 0, which gives me 2x, which shows you that whether you use x prime or whether you use x as your input, you get the same output. So it's single valued. So, okay, well defined. Is it a homomorphism? Well, apparently. So, why is it not a ring homomorphism? I said prove it's a group homomorphism in part B, right? Right. It's not a ring homomorphism because what? Doesn't preserve the unity is a good answer. The thing that's a perfectly good answer for this year, which I should accept. However, the definition of ring in 2016 did not assume identity.
Like in all of mathematics
Well,
or in
but
class?
ring homomorphism did.
No, not
Oh, okay, not in 2016.
not in the 20. In 2016, I was following Galian, who works with rings without unity. His ring is an RNG. But since our default meaning for ring was that it has an identity, and therefore that ring homomorphism has to map identity to identity, I like your reason for this not being a ring homomorphism even more, because that's much simpler than doing what I was doing here. Yeah. But I strike it down because it doesn't preserve the multiplication, is the other way. So not surprisingly, on our final exam, you should use our definitions, okay? Seem fair? All right, good. Let psi from G to H be a homomorphism of group. Prove that psi is injective if and only if the kernel of psi is equal to E. My goodness, if you're a student in 2016 and you didn't get this on the final, shame on you. Because in any semester, this is a gift. Right? Because this is like a central result of group theory, that a mapping homomorphism is injective if the kernel is the identity. We also had this theorem in linear algebra, right? The kernel is 0 if and only if the linear map is injective, right? So, and it's the same proof. So, any questions about this, or I'm going to go on? For I am tired. Ooh, hey, this one's fun. So there are various ways to prove this. I chose the lazy way, which is to use the determinate homomorphism. So determinate is a mapping from GLN to multiplicative positive, multiplicative real numbers, non-zero real numbers. It is, of course, a homomorphism, and its kernel is those matrices with determinant 1, which is exactly SLN. But we know that the kernel of a homomorphism is a normal subgroup of the domain. Therefore, SLN is normal in GLN. Yep.
This is the way you're intending us to solve this, right?
Yeah, but
Solving it any other way would take an unhealthy amount of time for the
I don't.
test.
It would take more time. It would still be possible, because all you got to do is let A be an element of SLN, let G be in the let G be an invertible matrix, look at G inverse, and give arguments to prove that's an SLN. Well, what do you have to do? The determinant of G inverse is the determinant of G, determinant of A, determinant of G inverse, but the G and G inverse determinants cancel out. You're left with the determinant of A, which by assumption was 1, therefore G inverse is in SLN. So you've shown that conjugation of SLN is a subset of SLN, which is to say that SLN is normal inside GLN. So the conjugation argument is not too bad here. It would even fit, and I wasn't displeased if students did that. But this is lazier. Yeah. Oh, and here we're proving that the, what's this called? Yeah, the stabilizer.
Oh, one last question.
Uh-huh.
Do we have to prove that, so in your proof right there, it's not, you proved that it was normal.
Right.
I don't think it didn't sound like you covered the fact that SLN was a subgroup. Do we have to prove that it's a subgroup as well? Like independent, like, the kernel, we know that's a normal subgroup.
It depends on the problem, whether or not it's expected for you to show that it's a normal subgroup. If in doubt, you should ask me about that on the final. Now here, I have proved that it's a subgroup because I've shown you that phi is a homomorphism, and we know that the kernel of a homomorphism is a subgroup.
Yes.
So that's
Yes.
the brute. That's
Conjugation argument.
yeah.
The conjugation argument would require
The conjugation argument. You're right. That would
extra subgroup.
still. I would still need to show that SLN is a subgroup. Good point. Yeah. You're right. So my conjugation argument is not as complete as this one. Yeah, I mean this kernel's a normal subgroup theorem is really slick. So the stabilizer being a subgroup. This is a good question on any test because it's relatively abstract, but it's not calculationally onerous, And so if you have a clear mind about how to prove something is a subgroup, this isn't that bad. Because what you have to do, of course, is to show it's a subset, but that's immediate because the stabilizer is taken to be a subset of G. And then you have to show that the identity's in there. Well, you don't have to show the identities in there, but showing the identities in there proves that it's not empty, right? So that's easy enough because E times X is equal to X is from the definition of group action. Therefore, E is in the stabilizer, so it's not empty. And if you take two things in the stabilizer, you can easily prove that their product is in the stabilizer using this sort of associative-like axiom for the group multiplication. My star and my X look too much alike here. But there it is, so that's scratched out. I didn't have white out at the moment. AB is in GX. So, and then the inverse is, you can get stuck on this inverse thing sometimes, but it's actually not bad. You just have to use your imagination. X is A times X, which is then by the associativity axiom again, A inverse A times X, which is E times X, which is X again, so A inverse times X is X. Therefore, A is in the inverse. So admittedly, this right here, sometimes students get stuck on, and I understand that. I do too sometimes, but that's not a bad question. Of course, now that I put it on the review, it's less likely to be on the final. Now you're asking yourself the question, is he joking?
For 17,
Yes.
we're
Uh-oh.
not counting the ways that you turn it inside out.
Yes, I think that was an ambiguity of the 2016 course. The question is, what does symmetries mean?
Like I say 24, but if I rip it inside out.
Right, so this really, to make the solution correct, we should cross out symmetries and put motions. Because a motion is a symmetry which is physically realizable. And of course, those inside-out ones are not. Unless the cube is, like that character on the Gifted. I don't know if you guys, guys don't watch. You don't watch TV, you don't know what I'm talking about. You know what I'm talking about? The Gifted, yeah, there's a character that turns stuff inside out.
Okay, never mind.
Like as soon as
I thought you were talking about Gifted, the movie.
as soon as they introduce this character, I'm like, oh, they got a character that turns things inside out. I'm like, she's gonna turn people inside out. It's gonna happen. So, yeah, it happened.
Oh, it did happen? That's
Yeah, they don't show it, but wait, what?
So I have a question.
So technically, if I don't change the wording here, I really should put 48 because, yeah.
So ripping it inside out doubles the orbit, correct?
Yeah.
So, but you can also change double the stabilizer by if you put a mirror in the corner from mapping from one corner to the opposite corner,
Uh-huh.
then and switch those,
Uh-huh.
then that doubles the stabilizer.
Yeah, I said the stabilizer was 8.
Yeah, that is what I said as well.
Because the orbit, technically, there's really only 6 different faces to move to, in my perspective.
Unless you rip it inside out. That's when the ripping it inside out matters, I think.
Well,
So we did.
Well, I had 2 stabilizers inside out.
I don't know, but what I do know is that there are 24 motions, but there are 48 symmetries. And I do think that the number of faces on a cube are 6, and that the group action is transitive. And that if you just focus on one face and allow yourself to turn it over, which means that you're turning the cube inside out, then that's just D4. It's just D4. It's the dihedral group on 4 things because it's got the 4 corners. So it's essentially just D4.
So you wouldn't have 8 for the stabilizer? Or it would be 12 for the orbit?
D4 has 8 elements, so the 6 times 8 is 48.
Okay.
The stabilizer. But if you can't turn it out, if you can't turn the face inside out or flip it over, you've just got the rotation. You've got the Z4 essentially. So then 4 times 6 by the orbit stabilizer theorem gives you the number of motions. I will, if I ask a question out that it will not be ambiguous on your final. I will use the word motions or the word symmetries. And if there is any doubt about that, please don't hesitate to ask me. Yep. So, yep. What it is? Questions or?
No, this makes a lot more sense now.
Yeah, after you do about 2 of them, they get boring, right?
Wait, what?
I mean, after you do I had one of these in your homework, right?
Oh.
And then you did another.
No,
Oh.
I thought it was isomorphic to Z2 cross Z2, but I didn't realize it said field. We were trying to find a ring that it said.
Oh. Yeah.
Ours did say ring.
Wait, did it really?
Yeah, ours said ring, not field.
Really?
Yes. So we use Z2 cross Z2.
Wait a minute. Do you mean to tell me this year I actually worked out my final before I gave it? No way. Where's the fun in that?
Yeah, it does say ring.
Oh. So I worked, so what the other one is my first draft. The solution is my first draft. Yes.
Everything else has been the same for a while.
Huh.
But I don't believe that ring exists if you're asking for a ring isomorphism.
Oh?
If you were looking for a group a ring which is additively homomorphic, or additively isomorphic as a group, then Z2 cross Z2 works.
The
But
multiplication
does not work.
doesn't match that Taylor table, but
And it also doesn't work in any sense of the term. There are a couple of terms for which it works.
I wanted it to work too.
It does not work.
But when I would put elements, oh yeah, you're right. I keep convincing myself that it was working. I convinced myself that it works. Because I didn't even.
Isn't it?
Wait, and so because it's not a field, you can't find a field that is isomorphic to, and so that's like it.
So, isn't it just the Klein 4 group? I mean,
Which is isomorphic to Z2 cross Z2. right?
yeah.
Yes, but there's not a group that's isomorphic both additively and multiplicatively. Which is what a ring isomorphism has to be. It has to preserve both multiplication There's not a group with 4 elements.
Huh.
There's not a ring with 4 elements that preserves both of those from what we can find.
That seems wrong to me.
So like the addition works fine, but for if you define the isomorphism to be, say, you have A plus IB plus J equals like the ordered pair AB.
I would think. So is it the case that 1 plus j times 1 plus j is j? Oh, so one is the additive identity. Excuse me, multiplicative identity.
Yes.
And what's I? Oh, okay. So you guys are sure this isn't Z4?
Because you can't get I from adding 1 to itself, no matter how many times.
Okay. Huh. So you guys don't think that there's an isomorphism? You think it's additively isomorphic to Z2 cross Z2, but not as a ring? Hmm.
And because the identity isn't mapped to the identity either. Because the identity would be 1 plus J. But, I mean, that was just for the one isomorphism, and that would map to 1.
Well, yeah, I guess. Okay, so again, this is 2016, so it's RNG, not. So like, but you're right. In our current realm, if you guys believe that it's isomorphic to what is this thing called? What do I call it? I was trying to find something less. So this thing, in Z2 cross Z2, right? Then you have to write. That is not up for grabs. And once you write that, if it doesn't work, you're out of luck. And
Oh yeah, that was what we were doing last night, wasn't it? That was what we were trying to help with that.
so what would be, is this an additive or a multiplicative, right? So like what's 1 plus j times 1 plus j?
1 plus J.
So that means that psi of 1 plus j squared is supposed to equal to 1 squared, right? Oh, which is true, okay. What's the problem then?
But no matter
Hey,
what,
one thing worked, why isn't it right?
That's what I'm saying.
no matter what you map I to, no matter what I does not hold under the isomorphism. If I is 1, 0, so mapping 0 to 0, mapping j to 0, 0, and mapping the identity to 1, 1, you're left with either 1, 0 or 0, 1. I squared leads to 1, whereas I.
So this is supposed to be like that, using the bar.
You also have to map to the identity.
And so, but you say I is 1?
Yes, II is -1, which is equal to 1 bar.
Right.
But if you take psi of I,
Mm-hmm.
then that leads you to one of the elements, say like without loss of generality.
So,
or
so it either.
it's like 1, 0.
So
then
this.
it'd be equal to itself.
So this either has to be 1, 0 or 0, 1.
But either way. we
Because
go by that.
because we already have 1, 1 for 1, and psi of 0
Yes.
is 0, 0. So that your choices are either that's that or that's that.
Yeah, so then when those are multiplied together, they equal themselves again. So they equal 1, 0 again. But
Uh-huh.
when you take, that leaves that one bar has to be the other one. And I squared is equal to 1, which under the isomorphism has to be the other one. So one
You mean you're talking about the 1 plus I one?
No. Oh, yes, sorry, yes. That's what I'm talking about.
So this, but the problem is that this plus this is 0, right?
Yes.
And so if this is 0, 1, 0, 1, if it maps to that,
Yes.
you're not able to get 0, 0 from that.
Right. That is one of the issues.
So this is, well, all right. Anyway, I think I'm convinced that you guys are correct that given our definition of ring this semester, maybe it's possible to find an RNG, but
Oh no, originally we had an RNG because we mapped,
an RNG homomorphism is what I meant to say, but yeah.
I think, is you originally mapped 1 plus j to 1, 0, right?
Yeah.
And then I plus j to 0, 1, and then 1 plus I to 1, 1, but that didn't work either. That didn't.
Interesting.
I failed for the same
Huh.
reason.
Huh.
So,
This is, I have to think more about that. Problem 19, commutative ring with identity, prove A is a unit if and only if A generates the whole ring. So if A is a unit, if you pick any x in the ring, then AA inverse x is an element of that, and therefore you just prove that anything in x is a subset of that, which means that, by the way, also we already know that this is a subset of that because it's, the structure of a ring. So we have, of course, that A is equal to R. On the other hand, if this is equal to R, that means that 1 is in the ring, and so there exists 1 in the ring. There exists a ring, R in the ring, such that A is equal to 1 is equal to A times R, which is to say that A is a unit. So, it's not a hard problem, right? But it tells me a lot. If I ask a question like this, actually, I learn a lot about students. I do. I do. Prove f of field, f of x is a principal ideal domain. This is something that had a lot more emphasis in the 2016 course than your course, but it's still a good question. Surjective homomorphism rings says unity. Prove that phi of 1 is the unity of S. See, this is an interesting problem, right? Because it seems like it's a tautology given your set of definitions, right? But the intended way this problem is to be read is, suppose it's a surjective homomorphism of ring RNGs, right? Sorry, I didn't fix it to make it more awful. If your solution is, well, it's a ring homomorphism, so psi of 1 is 1, I can't really complain because that was your definition, But you should look at this and understand that this was the intended solution, yeah? So the point is, if it's surjective and we pick Z and S, that means that there's something in Y, something in R called Y, such that phi of Y is equal to Z. But if we look at phi of 1 times Z, that's phi of 1 times phi of Y, which is phi of 1 times Y, which is phi of Y, which is Z. Therefore, you can see that phi of 1 serves as the multiplicative identity in the codomain. So, but yes, if I was to ask this question on the final, I would need to reword it a little bit. How many problems are on here?
A lot.
Ay, ay, ay.
We have 2 more pages. And this page is dead.
Dang it.
You can skip this one.
I want to go home.
So do we.
Okay, so this one's, you guys are cool on this one?
Yeah.
All right.
Easy.
Huh.
Is that 5 numbers? That's 5.
Huh.
Frac G.
I thought it was. I was like, stop. Okay, that is a 5.
All right.
I'm doing okay now.
Let's see here. R a commutative ring. I an ideal of R. Prove R mod I is commutative. So the definition of coset multiplication is you multiply representatives, but when the representatives commute, the cosets commute. Like so. So that wasn't bad. Although quotients of commutative rings and commutative, I can't read. It's not the case that quotients of an integral domain are integral domains. Give an example which illustrates this fact. So what do I got? I mean, there are many answers here, right? But this is Z is an integral domain. Obviously, mod 4Z gives me a quotient ring which has 0 divisors, like 2. Let's see here. Let R be an integral domain, S a subring of R which contains a multiplicative entity R, show that S must be an integral domain. All right, so if R is an integral domain, that implies it's a commutative ring with unity. And S, a subset of R, is also commutative. And we assume 1 is an S. And so if A, B are an S, and we put AB equal to 0, that means AB are an R, which means either A is equal to 0, B equals 0. Therefore, S has no 0 divisors. All right. So you just, it's not hard, right? You just have to work through it. Just kind of write it out. Part C says that subrings containing one of integral domains are themselves integral domains. The analogous statement does not hold for fields. Give an example of a subring containing one of a field which is not itself a field. So, all right. Obviously, integers are good examples. So this is the final one, right? Okay. All right. So I had the subgroup of S4 generated by this permutation 1, 3, 4. And I said find a real matrix representation of G is a subgroup G prime in GLNR, which is homomorphic to G. And if phi from G to GLNR is injective, with phi of G equal to G prime, then G prime is known as a faithful representation of G. So I wanted you to find a faithful representation of G inside GL4R. So what I did, I think that this proof follows Cayley's theorem. Is that right? Cayley's theorem? So 1 goes to 3, 3 goes to 4, 4 goes to 1, and 2 is fixed. That gives me this matrix. And if you look at that matrix, will generate a group of order 4, I think. Here's the explicit calculations. I mean order 3, excuse me. And there you go. G prime is that. The isomorphism from sigma to G prime should be clear. I think this problem is kind of like, what? From the perspective of your semester, but it was less out there for them.
Oh, that